In this video, we'd like to describe to you some of the work that we've done recently in the accompanying paper, Estimating Graphlet Statistics via Lifting. First, let's build some context. Networks are an extremely common data type, present in areas such as social networks, the internet, traffic, and genetics. And accordingly, many researchers are interested in studying the properties of these objects. Companies such as Facebook and other social media companies are, for example, interested in studying the behavior of their users. And as we've learned from FBI investigations, turns out that governments are as well. So accordingly, lots of network analysis tools have been developed. Some of these are degree distribution, eigenvector centrality, and Graphlet Statistics. Let's look at Graphlet Statistics. By Graphlet, what we mean is a small graph in the order of 5 nodes or fewer. By Graphlet Statistic, what we mean is choosing a family that is all graphlets of a particular size and getting the counts. Accordingly, a large number of exact count methods have been developed. Some of these are parallel graphlet decomposition and escape. But unfortunately, these methods hit the complexity barrier around k equals 5 for large graphs. That is, in graphs that are around size of a million nodes. Monte Carlo methods accordingly have been developed, which randomly sample and estimate the graphlet counts. Some of these methods are pairwise subgraph random walk and waddling. Our method belongs to the latter category. Our method is general. It is able to estimate graphlets of any size without procedure modification. It is parallelizable, and it has low variance. Let us describe the procedure. First, we randomly sample a node. Then we randomly sample one of its edges, add the corresponding node to our set, and if we wish to go further, now choose an edge from the general neighborhood of our set. And then, once we choose the node, we complete the induced subgraph. So in this case, if we were looking for 3 graphlets, we would stop and get a triangle. Otherwise, we'd go on. To complete the method, we have to weigh each graphlet type inversely by its probability of being sampled, and we show that this can be computed in closed form as a function of the number of degrees of the vertices in the sampled subgraph. We also prove that lifting is unbiased and has variance that scales with the max degree of the graph. We also experimentally demonstrate that lifting performs at the level of state-of-the-art methods and can scale to estimate k equals 6 graphlets of a 3 million node Facebook graph. We have code available on GitHub with Jupyter notebooks available, and we think that our method could be helpful for researchers interested in large graphlet statistics. Thank you for watching.